The last time human beings left Earth orbit, Richard Nixon was president, the Vietnam War was still being fought, and nobody on the planet owned a personal computer. That was December 1972, Apollo 17. Gene Cernan stepped off the lunar surface, climbed the ladder of the ascent module, and became the last human being to stand on the moon. He said a few words, looked back at the footprints he was leaving behind, and that was it. 50 years of silence. 50 years of humans circling the same 400-kilometer strip of low Earth orbit, going nowhere, going in circles, doing extraordinary work, but always within the same thin shell of atmosphere that has defined the accessible universe for every person alive today. That is about to change, and the mission that changes it is not a landing. It is something more elemental than that. Artemis II is going back to the moon, not to land, to orbit it, to swing around it and come back. And that sounds, if you let it, like a letdown, like a cautious half-step, a bureaucratic compromise between ambition and budget. But if you actually understand what Artemis II is, if you look at the engineering involved, the history it is being stacked against, the crew who are going to do it, the crisis that nearly stopped it before it started, and the geopolitical race that is now tighter and more dangerous than any space race that came before it, then the picture that emerges is not of a cautious mission. It is of the most audacious crewed spaceflight since the Apollo program, being conducted in the shadow of a problem that NASA initially tried very hard not to talk about. 4 human beings are going to climb into a capsule on top of the most powerful rocket ever flown and travel 370,000 kilometers from Earth. They are going to do this in a spacecraft that has flown exactly once, with a heat shield that developed a problem on its first flight that shocked the engineers who built it, on a rocket that has had 2 development launches each, with anomalies serious enough to delay the program by years. This video is about all of it, the mission itself, what Artemis II is actually going to do, minute by minute, day by day, the 4 people who are going to do it, the heat shield problem that NASA first described as expected, and that engineers subsequently described as the opposite of expected, the $93 billion program that is building the infrastructure for humanity's return to the moon, and why that number might be the least surprising thing about this entire story, and the race that is happening around all of this, the Chinese lunar program that is closer to landing on the moon than most people realize, and what it means that for the first time since the 1960s, the geopolitics of space exploration are genuinely urgent. We are going to start with the mission, and then we're going to work our way out to the world it is happening in. Chapter 1, The Mission. What Artemis II is actually doing. Artemis II is the second flight of the Space Launch System, NASA's new heavy-lift rocket, and the first crewed flight of the Orion spacecraft. It is currently scheduled for no earlier than April 2026, having been delayed from its original 2024 target. The mission profile is a free return trajectory around the moon, a specific type of lunar orbit that NASA calls a hybrid free return trajectory, lasting approximately 10 days. Let's break down exactly what that means. The mission begins at Kennedy Space Center in Florida. The crew of 4 boards the Orion spacecraft which sits at the top of the Space Launch System, a rocket that stands 98 meters tall and produces 8.8 million pounds of thrust at liftoff, more thrust than any rocket in history. The Saturn V, which took Apollo astronauts to the moon, produced 7.9 million pounds of thrust. The SLS is more powerful. It is the most powerful rocket ever successfully flown. At liftoff, the SLS burns for approximately 8.5 minutes to reach Earth orbit. The core stage, which burns 4 RS-25 engines, the same engines used on the Space Shuttle, refurbished and modified, exhausts its propellant and separates. The interim cryogenic propulsion stage, a modified upper stage also called the ICPS, then burns to circularize Orion's orbit at approximately 30 by 1,800 kilometers, an elliptical parking orbit. The crew spends several hours in this parking orbit running system checks, confirming that everything on the spacecraft is functioning correctly before committing to translunar injection. If everything checks out, and this is one of the key differences between Artemis II and the Apollo missions, the crew has a go/no-go decision point before leaving Earth orbit. The ICPS fires again to perform the translunar injection burn. This burn, lasting approximately 5 minutes and 40 seconds, accelerates Orion from its orbital velocity to a velocity sufficient to escape Earth's gravity and travel to the moon. After the TLI burn, the ICPS separates and Orion is on its own. The journey to the moon takes approximately 3 days. During transit, the crew performs daily health checks, exercises to maintain cardiovascular fitness. The same problem of deconditioning that afflicts astronauts on long missions applies even over 3 days. Monitors spacecraft systems and conducts experiments and observations. The transit is not a passive phase. The spacecraft is actively communicating with mission control at Johnson Space Center in Houston through the Deep Space Network, a global system of large radio antennas that provides communication coverage for spacecraft beyond Earth orbit. At the moon, Artemis II does something specific and technically interesting. Rather than entering lunar orbit in the conventional sense, which would require a burn to slow down and be captured by the moon's gravity, Artemis II uses a hybrid free return trajectory. The spacecraft swings around the far side of the moon at an altitude of approximately 8,900 kilometers above the lunar surface, using the moon's gravity to sling itself back toward Earth. This trajectory is called free return because if the spacecraft does nothing, if the engines fail entirely after the lunar flyby, it will return to Earth naturally, pulled back by Earth's gravity without any additional burns. This is a deliberate safety feature. The free return trajectory means that the mission can abort at specific key points and still return the crew safely to Earth without requiring any propulsive maneuver. The Apollo 13 mission, which suffered a catastrophic oxygen tank explosion on the way to the moon in 1970, survived precisely because the crew used a free return trajectory to sling around the moon and coast back to Earth after the explosion disabled most of the spacecraft's systems. Artemis II is designed to have this same escape route available. The far side passage of the moon is the defining moment of the mission. At closest approach, the crew will be approximately 370,000 kilometers from Earth, farther from home than any human being has ever been. The record for the farthest humans have ever traveled from Earth was set on Apollo 13 at approximately 400,171 kilometers from Earth. And that was because the explosion and the emergency-free return trajectory took them further than planned. Artemis II's crew will approach that record, though the specific distance depends on the exact trajectory flown. What they will experience is something no human has experienced since 1972. The view of the moon close up, the view of the Earth as a marble in the blackness, and the total silence of the far side of the moon, out of radio contact with Earth, in the most remote location any human being has occupied since Gene Cernan left. After the lunar flyby, Orion coasts back toward Earth over approximately 3 days, decelerating due to Earth's increasing gravitational pull. The crew continues to monitor systems and conduct experiments. The return trajectory is designed to bring Orion back to Earth at the correct angle for atmospheric re-entry. This angle is critical, as we will discuss in detail later. Re-entry is the most dangerous phase of the mission. Orion enters the Earth's atmosphere at approximately 39,000 kilometers per hour, roughly 11 kilometers per second, compressing the air ahead of it so violently that the temperature of the compressed air reaches approximately 2,760 degrees Celsius. The crew is protected by the Orion heat shield, a disk of material attached to the bottom of the capsule, 5 meters in diameter, the largest heat shield ever flown on a crewed spacecraft. After the heat shield slows the capsule in the atmosphere, parachutes deploy to bring Orion to a gentle splashdown in the Pacific Ocean off the coast of San Diego, where a recovery ship and diving teams from the U.S. Navy will retrieve the crew. The entire mission duration, from liftoff to splashdown, is approximately 10 days. Chapter 2. The crew, 4 people making history. The 4 people who are going to make this journey are not accidental choices. Each of them represents something specific, a deliberate statement about what the Artemis program is and who it is for. And each of them has a personal history that makes the selection feel, in some cases, like a kind of cosmic poetic justice. The crew was announced on April 3, 2023, by NASA Administrator Bill Nelson at Johnson Space Center. It consists of Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. Reed Wiseman is the mission commander, and he is in some ways the most conventional choice of the 4, which is not to say conventional in any ordinary sense. Wiseman is a U.S. Navy test pilot and NASA astronaut who has previously flown to the International Space Station. He served as commander of a long-duration expedition to the ISS in 2014, spending 167 days aboard and performing 2 spacewalks. He is 48 years old at the time of this recording, a graduate of Johns Hopkins University in computer engineering with a master's degree from the U.S. Naval Postgraduate School in aeronautical engineering. He is, in the precise technical sense, the right person to command a mission of this complexity. Experienced with long-duration spaceflight, trained in systems management under pressure, and a test pilot by background, which means his professional career has been built on evaluating new vehicles in risky conditions and reporting back accurately on what they find. Victor Glover is the pilot, and his role in this mission is historic in a way that deserves more than a passing mention. Glover will be the first Black astronaut to fly beyond low Earth orbit. let that land for a moment. The United States has been flying humans in space since Alan Shepard in 1961. 65 years of human spaceflight history. In that entire history, no Black American has traveled beyond Earth orbit. Not during Apollo, not during the shuttle era, not during the current ISS era. Glover is going to change that, and the significance of this goes far beyond the symbolic. It is a statement about who space exploration belongs to, and it arrives at a moment when that question has never been more contested. Glover is 47, a U.S. Navy pilot and a NASA astronaut who flew on Crew Dragon as the pilot of Crew 1 in November 2020, spending 168 days on the ISS. He is a graduate of California Polytechnic State University with a master's degree from Air University, the Naval Postgraduate School, and the Air Force Institute of Technology. A man who has spent his career accumulating qualifications in the most demanding domains. He will be 48 by the time Artemis II flies. He will be, at that moment, the farthest from Earth of any Black human being in history. Christina Koch is the mission specialist for Artemis II, and she is already a record holder. Koch holds the record for the longest single spaceflight by a woman in history, 328 days on the International Space Station in 2019 to 2020. During that mission, she performed the first all-female spacewalk in history, alongside astronaut Jessica Meir. She is a former Peace Corps volunteer, a former Antarctic field researcher, an electrical engineer with a graduate degree from North Carolina State University. She is 45, deeply experienced in long-duration spaceflight, and she is going to be the first woman in history to travel to the moon. Christina Koch will also be the first person to go to the moon who did not grow up knowing that going to the moon was something that women could do. Every woman who is a child today will know that going to the moon is something women can do, because Koch is going. The symbolic weight of this is genuinely enormous, and it is worth saying clearly. The Artemis program's commitment to flying a diverse crew is not a public relations exercise. It is a structural choice that changes what the also history of space exploration looks like, and it changes who the next generation of space explorers will be. Jeremy Hansen is the fourth member of the crew, and he is Canadian. A Canadian Space Agency astronaut and Royal Canadian Air Force colonel, Hansen is the first person who is not American to fly beyond low Earth orbit. Not a Soviet, not a Russian, not a European, not a Japanese astronaut, a Canadian. For an agency that has contributed enormously to space exploration through the Canadarm and its successors. Through the contributions of astronauts like Chris Hadfield, through decades of partnership with NASA and other space agencies. This is the moment when Canada's role in human spaceflight takes a leap that no one in the 1990s, when the Canadian Space Agency was first getting serious about human spaceflight, could have specifically predicted. Hansen is 48, a test pilot by training who has never previously flown in space. Artemis II will be his first space flight. This is unusual. The Apollo commander Alan Shepard had previously flown on Mercury. The Apollo 11 crew had collectively accumulated enormous spaceflight experience. Flying a first-time astronaut on a mission of this risk level is a choice that reflects two things simultaneously. the relative scarcity of astronaut candidates with previous beyond LEO experience. There is none, since no one has gone beyond LEO since 1972, and the confidence that NASA has in the Orion spacecraft system and in Hansen's training as a test pilot. These 4 people are going to strap themselves into a spacecraft that has made 1 flight, sit on top of a rocket that has made 2 flights, and travel farther from Earth than any human being has in 52 years. That context matters. It sets the stakes. Chapter 3: The Heat Shield Controversy. The problem NASA didn't want to talk about. In November 2022, the Orion spacecraft completed the Artemis I mission, an uncrewed test flight around the Moon. The first flight of the Space Launch System, the first flight of the Orion spacecraft. The mission was considered a success. The rocket flew. The spacecraft made it to the Moon and back. The splashdown happened on December 11th, 2022, and NASA held a press conference that described the mission as having met all its primary objectives. And then, over the following months, engineers began looking more carefully at the heat shield. The Orion heat shield is not a ceramic tile system like the space shuttles. It uses a material called Avcoat, which is the same material used on the Apollo Command Module heat shields in the 1960s. Avcoat is an ablative material. It works by burning away, absorbing enormous heat in the process, protecting the interior of the spacecraft from the thermal environment of re-entry. As it burns, it chars and ablates. It physically erodes, and this is by design. The question after Artemis I's return was whether the ablation was occurring as expected. The data was not reassuring. February 2023, NASA confirmed that the Orion heat shield had experienced significant material loss during re-entry. Loss that was greater than what the models had predicted. More specifically, the heat shield had experienced what engineers described as unexpected char loss patterns, regions where the Avcoat material had cracked and ejected chunks of material during re-entry, rather than ablating smoothly as designed. The cracking and charring was not uniform. It was patchy, with some areas performing as expected and other areas showing a type of material behavior, described technically as the char layer failing in an unexpected mode, that had not been seen in ground testing. NASA's initial public communication on this issue was, to put it charitably, understated. In the weeks following the initial confirmation that an anomaly existed, the agency described the phenomenon as within acceptable limits, and suggested that the team was investigating to ensure they understood what had happened before the crewed mission flew. The language was calm. The framing was reassuring. Then, in the summer of 2023, the details started emerging in the NASA Inspector General report and in the testimony of engineers speaking to the House Science, Space, and Technology Committee. The picture that emerged was more troubling than the initial public statements had suggested. The char loss was not a minor statistical variation from the models. It was an unexpected mode of failure, a physical process that the engineers had not predicted, that had not been observed in any of the ground-based testing that was supposed to validate the heat shield design, and that could not, at the time of those statements, be fully explained. The working hypothesis was that the unexpected charring behavior was related to the specific re-entry profile flown by Artemis I. which was a skip re-entry, a new technique in which the spacecraft skips off the upper atmosphere like a stone on water before making its final plunge, allowing it to modulate the heating rate and target a specific splashdown zone. The skip re-entry is a planned technique for all Artemis missions, and it produces a specific heating profile that differs from the more direct re-entries used on Apollo. The hypothesis was that the skip re-entry's heating profile, the specific pattern of how the heat is applied to the heat shield over time, with the skip creating a period of lower heating followed by a period of higher heating, may have contributed to the unexpected charring mode. During the skip, the char layer that had already formed cooled somewhat and potentially became more brittle, so that when the final re-entry heating resumed, the char layer fractured and ejected rather than ablating smoothly. If this hypothesis is correct, it has a specific and deeply uncomfortable implication. The skip re-entry is not an optional feature of the Artemis missions. It is the planned re-entry profile for every Artemis flight. It is the technique that allows Orion to target specific splashdown zones, and that provides the aerodynamic capability to handle the higher return speeds expected from future lunar surface missions. If the skip re-entry is causing unexpected heat shield behavior, then the problem is not isolated to Artemis I. It is potentially present on every future Artemis mission, including the crewed one. Artemis II. A critical additional wrinkle. The re-entry speed for Artemis II will be comparable to Artemis I. But when Artemis III eventually attempts a crewed lunar landing and return, the spacecraft will return from the moon at higher velocity, closer to the lunar return velocity than the Artemis I trajectory, which was on a slightly different profile. The heat shield is designed for the highest velocity return. The question is whether it behaves as designed when the actual thermal environment differs from what was modeled. NASA announced in October 2023 that it was conducting a detailed investigation into the heat shield anomaly, and that Artemis II would not fly until the investigation was complete and the team was confident the risk was acceptable for a crewed mission. This was the right decision. It was also a significant admission that the heat shield had not performed as expected, that the models had been wrong in a way that was not fully understood, and that the team needed to understand why before putting 4 human beings inside the capsule. The investigation continued through 2024. The NASA Inspector General, in a report released in November 2023, delivered a sharply worded assessment that questioned whether the agency had been sufficiently transparent about the anomaly in its initial public communications, and noted that the testing program for the heat shield had not been designed to catch this specific type of failure mode. The Inspector General also raised concerns about the timeline for resolving the anomaly and about whether the Artemis program's schedule pressure, the political and institutional pressure to fly the crewed mission, was being weighed appropriately against the safety requirements. The congressional testimony in early 2024 added important texture to the public record. Several engineers who had worked on the heat shield investigation, speaking through prepared statements to the House Science Committee, characterized the anomaly in terms that were noticeably more alarming than the agency's official communications. One characterization, from a senior engineer involved in the investigation who was not identified by name in the public record, described the Shar ejection events as anomalous in the sense that they represent a physical phenomenon we did not anticipate and did not test for. The distinction between unexpected but acceptable and anomalous and not yet understood is not semantic. It is the difference between a known margin of uncertainty and an unknown one. And for a human spaceflight program, that distinction matters enormously. The NASA Inspector General, Paul Martin, testified directly that his office's review of the investigation timeline found that the agency had not communicated the full scope of the anomaly to the public in a timely manner. The report noted that the initial characterization of the heat shield performance as within limits was technically accurate by the agency's own criteria. The heat shield had not failed in the sense of breaching and allowing the spacecraft to burn, but was potentially misleading in that it did not convey that the performance was significantly different from what models predicted, and that the difference was not yet understood. The Inspector General noted that this kind of communication gap between technically accurate and fully transparent is exactly the pattern that has preceded major safety failures in NASA's history. The decision to fly Challenger despite known O-ring concerns, the decision to re-enter Columbia despite known foam strike damage. The comparison to Challenger and Columbia was not made lightly, and it was contested by the agency. NASA's position was that the heat shield anomaly was being taken seriously, investigated rigorously, and that the agency would not fly the crewed mission until it was confident the risk was acceptable. The Inspector General's point was not that Artemis II would fail, but that the pattern of minimizing an anomaly's severity in public communications was a process failure, independent of whether the anomaly itself was ultimately found to be dangerous. NASA's position, as of the most recent available information, is that the investigation has identified the cause of the anomaly as related to the interaction between the skip re-entry heating profile and the thermal properties of the AV-coat char layer. Specific modifications to the re-entry trajectory, adjustments to the skip angle and the timing of the final re-entry maneuver are being evaluated as potential mitigations. The agency has stated that it will not fly Artemis II until the team is satisfied that the risk to the crew is within acceptable bounds. What within acceptable bounds means for a mission that is, by its nature, at the frontier of what crewed spaceflight can do is a question that deserves honest engagement. Every crewed spaceflight carries risk. Apollo 1 killed 3 astronauts on the launch pad. Challenger and Columbia killed 14. The Orion spacecraft's heat shield failure on Artemis I was not a near miss in the sense that the crew would have been killed. The Artemis I mission was uncrewed. But the fact that an unexpected failure mode was discovered on the first flight of a spacecraft that is about to carry 4 people in the most safety-critical phase of the mission is not a footnote. It is a fundamental engineering question that the team is working to answer, and it is one of the most important reasons that Artemis II has been delayed. Chapter 4: The Space Launch System, the most powerful and most controversial rocket ever built. The Space Launch System, SLS, has a reputation that precedes it, and the reputation is mixed. On one side, it is the most powerful rocket ever successfully flown, and it flew. The first launch on November 16, 2022, after years of delays, was successful. The rocket performed. On the other side, it took 17 years to develop from program inception to first flight at a cost of approximately $23 billion for the rocket alone. And it is the only rocket in history that is explicitly designed to be expendable, meaning every rocket is destroyed after one use, while costing approximately $4.1 billion per launch. Those numbers deserve context because they are astonishing. The Saturn V, the rocket that took Apollo astronauts to the moon in the 1960s and 1970s, cost approximately $185 million per launch in 1960s dollars, which adjusts to roughly $1.4 billion in 2024 dollars. The SLS costs approximately $4.1 billion per launch. It is approximately 3 times more expensive than the Saturn V in inflation-adjusted terms. And it carries similar payload capacity. The comparison to SpaceX's Starship is equally striking. SpaceX's Starship system, which first flew to orbit in June 2024, is designed with the explicit goal of reusability. Both the Super Heavy booster and the Starship upper stage are designed to be recovered and reflown. The projected cost per launch for a reusable Starship, according to SpaceX's own estimates, is somewhere between $10 million and $100 million, depending on assumptions about flight rate and reusability, which would represent an improvement of between 40 and 400 times over the SLS's per launch cost. Even the most pessimistic estimate for Starship's eventual cost is dramatically lower than the SLS's current cost. This cost differential is not an abstract concern. It shapes everything about the pace and ambition of the lunar program. The SLS is currently manifested for approximately 4 flights per year at maximum cadence, a cadence that has never been achieved, and that the program's own Inspector General reports describe as optimistic given the current production and refurbishment infrastructure. At 4 flights per year at $4.1 billion per flight, the annual cost of just flying the rocket, not including the Orion spacecraft, the Lunar Gateway, the Human Landing System, or any of the mission-specific costs, would be $16.4 billion per year. The entire NASA budget in 2024 was approximately $24 billion. Artemis, if it flies at even a fraction of its theoretical cadence, consumes a significant fraction of NASA's total resources. Why does the SLS cost so much? Several reasons, none of them satisfying. The first is the political economy of the program's origin. The SLS was created in 2011 by a congressional directive that required NASA to build a heavy-lift rocket using existing shuttle-era hardware and workforce. The 4 RS-25 engines on the SLS core stage were Space Shuttle main engines, extraordinarily sophisticated and expensive engines that cost approximately $146 million each to produce. On the Space Shuttle, these engines were recovered after each mission and refurbished for reuse. On the SLS, they are thrown away with the core stage. The decision to throw away $146 million engines on every flight was made partly because the SLS development timeline and budget did not accommodate the additional engineering required to make the core stage recoverable. The second reason is that the SLS lacks price competition. The program has been managed under cost-plus contracts with a small number of prime contractors, Boeing is the prime for the core stage, and Northrop Grumman builds the solid rocket boosters. Cost-plus contracting means that the contractor is paid its costs, plus a fixed fee, regardless of how efficiently the work is performed, which eliminates the price pressure that competitive fixed-price contracts would create. NASA's Inspector General has repeatedly identified cost-plus contracting as a primary driver of cost overruns in the SLS program. The third reason is heritage. The decision to use shuttle-era hardware and workforce was made partly to preserve jobs at specific NASA centers and contractor facilities that would otherwise have been at risk after the shuttle program ended in 2011. This is not a cynical observation. It reflects a real political reality in which NASA's budget is set by a Congress that represents, among other constituencies, the workers at Boeing's Michoud facility in New Orleans, at Northrop Grumman's facility in Utah, and at the NASA centers in Alabama, Texas, and Florida. The SLS program is, in part, a jobs program for the aerospace industry in specific congressional districts. And this shapes what the rocket costs and how it is built. None of this changes the fact that the SLS flew and worked, but it sets the context for understanding the pressure that the Artemis program is under. Both the pressure to fly on schedule, which contributes to the heat shield situation, and the pressure that comes from a launch cost that is simply incompatible with a sustainable, high-cadence lunar program. Chapter 5. The cost, $93 billion and counting. The NASA Office of Inspector General released a report in November 2021 that has become one of the most cited documents in the history of space program cost analysis. It calculated that the cost to conduct the first Artemis lunar landing, originally scheduled for 2025, now expected no earlier than 2026 at the earliest, would be approximately $93 billion. This figure encompasses the development costs for the SLS, the Orion spacecraft, the exploration ground systems, the launch infrastructure at Kennedy Space Center, and the human landing system, the spacecraft that will actually land on the moon, accumulated from 2012 to 2025. $93 billion. To put that in context, the entire Apollo program, from President Kennedy's 1961 announcement to the last moon landing in 1972, cost approximately $257 billion in 2024 dollars. Including the development of the Saturn V, the Apollo Command and Service Module, the Lunar Module, the entire ground support infrastructure, and 6 lunar landings. The Artemis program is projected to spend $93 billion to conduct 1 lunar landing, with more to come for subsequent flights. The Inspector General did not express this as a simple cost comparison. The report noted several specific concerns about the program's cost trajectory. First, the report identified that NASA was paying Boeing approximately $2.8 billion per year to develop and produce the SLS core stage, while producing at most 1 core stage per year, and more recently, less than 1. This means the program is paying the equivalent of roughly $3 billion per rocket in standing Army costs alone. The cost of maintaining the workforce and facilities, even when they are not producing flight hardware. Second, the report identified that NASA's cost estimates for the Artemis program had consistently underestimated the true cost of each element. The SLS was originally budgeted at approximately $6.8 billion for development and first flight. The actual cost was approximately $23 billion. The Orion spacecraft was originally budgeted at approximately $6 billion. The actual cost has exceeded $20 billion. The exploration ground systems were originally budgeted at approximately $2.8 billion. The actual cost has exceeded $3.5 billion and continues to rise. Third, the report noted that the cost per mission for the Artemis program, defined as the total cost divided by the number of missions flown, was expected to remain extremely high for the foreseeable future because the fixed infrastructure costs are enormous relative to the number of missions flown per year. In the OSL Apollo era, the program flew 6 missions in 3 years. The Artemis program is planning to fly at most 1 or 2 missions per year, spreading the fixed costs over fewer flights. The human landing system deserves specific attention because it represents both one of the most interesting and one of the most commercially innovative elements of the Artemis program. NASA selected SpaceX's Starship as the human landing system for Artemis II, the first crewed lunar landing, in April 2021 in a decision that shocked Blue Origin and Dynetics, the 2 other competing bidders. The selection of Starship was controversial because Starship, at the time of selection, had never reached orbit. It had not completed a full-duration engine test at scale. It was a vehicle that existed primarily in renders and engineering plans, but the selection made sense from a cost perspective. SpaceX's bid for the Human Landing System contract was $2.89 billion, dramatically lower than Blue Origin's $5.99 billion bid and far below NASA's own cost estimates for a government-developed lander. NASA chose the lowest bidder for a mission-critical element, an approach it has not always taken with major human spaceflight hardware. The irony, and it is a rich one, is that the vehicle that was selected for cost reasons may be the vehicle that eventually challenges the entire cost structure of the Artemis program. If Starship achieves its reusability goals and reaches the low per-launch costs that SpaceX projects, it will be substantially cheaper to fly a crewed mission on Starship than to fly one on SLS and Orion. This has led some in the space policy community to ask whether the SLS and Orion architecture, built at enormous cost to be the backbone of the American return to the moon, might be partially or eventually replaced by the very commercial vehicle it is relying on for its most critical element. NASA's current position is that SLS and Orion will continue to be the primary crew launch system for the foreseeable future, while Starship serves as the human landing system. The 2 systems are complementary in the near term. Whether this remains true as Starship's capabilities and cost profile develop is a question that will be answered by events rather than by any plan currently in existence. Chapter 6: The Orion Spacecraft. What's actually inside? Before diving into the race that surrounds all of this, it is worth spending time on the machine that is going to carry 4 human beings farther from Earth than any human has gone in 50 years. Because Orion is genuinely extraordinary. A spacecraft designed from scratch in the post-Columbia era, incorporating every lesson the agency learned from 30 years of flying humans in space. And because understanding what it is made of and what it can do is essential for understanding both the mission's ambitions and its vulnerabilities. The Orion spacecraft has two primary modules. The crew module, the capsule where the crew lives, works, and is protected during launch, re-entry, and splashdown, is 5 meters in diameter at its base, 3.3 meters tall, with a pressurized volume of 8.95 cubic meters for the crew. That is roughly the interior volume of a large minivan, shared between 4 people for 10 days. The Apollo Command Module had a pressurized volume of approximately 6.2 cubic meters for 3 people. So Orion is somewhat more spacious per crew member, though it is carrying 1 more person. The European Service Module, built by the European Space Agency as Europe's primary contribution to the Artemis program, provides the main propulsion, electrical power, thermal control, and oxygen and water for the crew module. The service module carries 8,600 kilograms of propellant, provides 26.7 kilonewtons of thrust from its main engine, an engine originally developed for the Space Shuttle's orbital maneuvering system, and generates electrical power from 4 solar arrays that extend from the service module like the spokes of a wheel, each array 7 meters long. Orion was designed from the outset with a specific set of safety features that distinguish it from previous crewed spacecraft. The most visible is the Launch Abort System, a tower mounted at the top of the crew module containing solid-fueled rocket motors that can pull the crew module away from the rocket in any emergency from the launch pad through the first stage of flight. The LAS can take the crew module from 0 to 130 kilometers per hour in approximately 1.8 seconds, an acceleration of approximately 20 g. It is not a comfortable experience. It is designed for exactly one scenario, getting the crew away from an exploding rocket. The abort capability extends throughout the flight profile, not just at launch. During the trans-lunar injection burn and transit to the moon, the service module's main engine can be used to return the crew to Earth if an abort is required. During the lunar, flyby, and the return transit, the free return trajectory provides passive safety. During re-entry, there is no active abort capability. Once the spacecraft is committed to re-entry at 39,000 kilometers per hour, the physics takes over. This is what makes the heat shield so critical. It is not a redundant system. It is not something you can work around if it fails. It is the only thing between the crew and temperatures that would destroy the capsule. The avionics on Orion are substantially more modern than Apollo. The spacecraft uses a star tracker for navigation, a digital fly-by-wire control system, and a distributed computing architecture that provides redundancy at multiple levels. The displays in the crew module are large touchscreen interfaces, familiar to anyone who has used a modern tablet computer, rather than the analog gauges and switches of Apollo. The crew can manually control the spacecraft through hand controllers, but in normal operations, the spacecraft flies itself, with the crew monitoring and intervening as needed. Life support is provided by the Environmental Control and Life Support System, ECLSS, which maintains cabin pressure, temperature, and atmospheric composition, removes carbon dioxide and trace contaminants from the cabin air, and manages water for the crew. Orion's ECLSS is designed for 21-day missions, the current maximum planned duration, and carries sufficient consumables for approximately 30 days of crewed operation, providing a margin of safety against extended missions due to contingencies. One aspect of Orion's design that does not always receive sufficient attention is its radiation protection. Beyond low Earth orbit, the Earth's magnetic field no longer provides the shielding against galactic cosmic rays and solar energetic particles that it provides for the International Space Station. The crew of Artemis II will be exposed to a radiation environment significantly more intense than ISS astronauts experience, and significantly more intense than what has been shown to cause long-term health effects in some models. The Orion spacecraft provides some radiation shielding from its structure and from the placement of water supplies. Water is an effective radiation moderator, but it cannot eliminate the radiation exposure. The 10-day duration of Artemis II is short enough that the cumulative radiation dose is expected to be within the acceptable limits established by NASA's radiation exposure guidelines. But those guidelines themselves are based on statistical analyses of cancer risk, not absolute safety thresholds. And the dose-response relationship for space radiation is still an active area of research. The radiation exposure that the crew of Artemis II will receive is one of several factors that make this mission's 10-day duration the appropriate scale for this phase of the program. Longer stays beyond low Earth orbit accumulate more radiation dose, require more consumables, and impose greater psychological strain on the crew. The 10-day Artemis II mission is long enough to accomplish its objectives and gather the operational data needed for subsequent missions, and short enough that the health risks from radiation and confinement are manageable. Chapter 7: The Operations Challenge. Flying in the 2020s versus the 1960s. One of the less discussed dimensions of the Artemis program is how different operating in deep space in the 2020s is from operating in deep space in the 1960s, and not always in the ways you might expect. Some things are dramatically better, some things are more complicated. The most important improvement is communications. The Apollo missions communicated with Earth through the Manned Space Flight Network, a collection of ground stations, some of which were relatively modest facilities in remote locations. The famous Honeysuckle Creek and Parkes radio observatories in Australia and the Goldstone Station in California were the key nodes for Apollo lunar communications. Communication during the Apollo missions was intermittent. There were periods when no ground station had line of sight to the spacecraft, and communication was lost. The far side of the Moon, where no Earth-based station has direct line of sight, was always a communication blackout. Artemis II will use the Deep Space Network, NASA's global system of large antenna facilities in California, Spain, and Australia, for primary communication. The DSN provides much higher bandwidth than the Apollo-era manned space flight network, allowing the transmission of high-definition video and data streams that were simply not possible in the 1960s. The crew will be able to communicate with mission control more reliably and with more data than Apollo crews could. They will have access to medical monitoring systems that transmit physiological data in near real time. They will be able to conduct video conferences with family members in a way that was impossible for Apollo crews. The far-side communication blackout remains a constraint. When Orion is behind the Moon, it is out of radio contact with Earth. This is not a surprise. It was true for Apollo 2, but it is a constraint that future Artemis missions with longer stays near the Moon will need to address. The Lunar Gateway, a planned small space station in cislunar orbit that is part of the long-term Artemis architecture, is designed in part to provide relay communication capabilities in orbits that provide more continuous coverage of the lunar surface and the surrounding space. The most important complication of operating in deep space in the 2000s compared to the 1960s is the regulatory and programmatic complexity. The Apollo program was operated by a single agency, NASA, with military precision and essentially no commercial involvement. The Artemis program involves NASA, the European Space Agency, the Canadian Space Agency, JAXA, and multiple commercial partners, Boeing for the SLS core stage, Northrop Grumman for the solid rocket boosters, Lockheed Martin for the Orion spacecraft, and SpaceX for the human landing system, among others. Coordinating across this network of stakeholders, each with their own contracts, schedules, and technical requirements, is a management challenge of a different order from the Apollo program. The commercial involvement is not uniformly a complication. SpaceX's development of the human landing system, funded by the relatively modest $2.89 billion contract, has produced a vehicle, Starship, that would cost many times more if developed under a traditional cost-plus government contract. Commercial competition, where it exists in the Artemis architecture, drives cost and performance in ways that the traditional government contracting model does not. But the integration of commercial elements into a government-led human spaceflight program creates interfaces and dependencies that add complexity to an already extraordinarily complex mission. There is also the question of operational experience. The Apollo program flew 16 crewed missions in 6 years. The development of operational procedures, the refinement of training protocols, the accumulation of hard-won experience with the specific quirks of the hardware happened at a pace that is not being replicated in the Artemis program. Artemis II is only the second flight of the SLS and the second flight of Orion. The crew will be flying on hardware that has been to space once. Mission controllers will be operating a flight control infrastructure that has been used for exactly one flight. The procedures, the workarounds, the subtle lessons that experienced crews and flight control teams accumulate over many flights, those are in very short supply. This is, in a sense, the price of the 50-year gap. The Apollo program built institutional knowledge rapidly because it flew rapidly. The Artemis program is starting from a much lower base of operational experience despite having far more sophisticated technology. The crew of Artemis II will in some ways be doing something more dangerous than the Apollo crews, not because the hardware is worse, but because there are far fewer flights of experience behind them. Chapter 8, the Chinese Lunar Program. The race is real. The narrative around the Artemis program tends to focus inward, on the engineering, the cost, the schedule, the institutional dynamics of NASA and its contractors. And that inward focus is understandable, because those are the immediate operational realities. But Artemis does not exist in a vacuum. It exists in a world where, for the first time since the Apollo era, another spacefaring nation is making a genuine, well-funded, technically credible attempt to send human beings to the moon. And unlike the Soviet lunar program of the 1960s, which was real but was characterized by secrecy, internal competition, and ultimately a loss of political will that prevented it from flying humans, the Chinese lunar program is public, coherent, well-resourced, and on a timeline that is genuinely competitive. The China National Space Administration's lunar program goes by the name Chang'e, named after the moon goddess of Chinese mythology. And it has been building toward crewed lunar operations for more than 15 years in a methodical, incremental way that closely mirrors the approach NASA used in the lead up to Apollo. The Chang'e 1 and Chang'e 2 missions in 2007 and 2010 were lunar orbiters. Chang'e 3 in 2013 landed a rover on the moon, the first soft landing on the moon since the Soviet Luna 24 in 1976. Chang'e 4 in 2019 achieved the first ever soft landing on the far side of the moon, a technically challenging accomplishment that required a relay satellite, Queqiao, positioned at the Earth-Moon L2 point to provide communication with the lander on the lunar far side. Chang'e 5 in 2020 landed on the Oumuamua moon, collected 1.73 kilograms of lunar samples, and returned them to Earth, the first lunar sample return mission since the Soviet Luna 24 in 1976, and the first by any nation in 44 years. This is not a slow program. In the span of 13 years, China went from its first lunar orbiter to a successful sample return, a sequence that, in compressed form, mirrors the development sequence NASA used for Apollo over a similar period. The Chang'e program is now in the phase that directly precedes human missions. Chang'e 6, which launched in May 2024, landed on the far side of the moon at the South Pole Aitken Basin, one of the most scientifically important sites on the moon, a massive impact crater thought to contain material from the lunar mantle, and returned samples to Earth in June 2024. This was the first sample returned from the lunar far side in history, and the success of the mission demonstrated that China's sample return technology is mature and repeatable. It also demonstrated the operational maturity of the Queqiao 2 relay satellite, which was launched in March 2024, specifically to support Chang'e 6 and subsequent far-side missions. Chang'e 7, planned for approximately 2026, will target the lunar South Pole, the same region that NASA is targeting for Artemis II. Chang'e 7 will include an orbiter, lander, rover, and a small flying probe designed to search for water ice in permanently shadowed craters. This mission is a direct scientific precursor to the Chinese crewed lunar program, gathering the surface data and establishing the operational experience at the target region. Chang'e 8, planned for approximately 2028, will take this further with in situ resource utilization experiments, attempting to use lunar regolith to create useful materials like bricks or oxygen, the same kind of technology that will be essential for a sustainable human presence on the moon. The Chinese crewed lunar program, known as the Lunar Exploration Phase 4, or sometimes described under the broader framework of China's human spaceflight program, has publicly stated an ambition to land Chinese astronauts, taikonauts, on the moon by 2030. This is an aggressive timeline that most outside analysts initially regarded with some skepticism. But the evidence of the last 5 years, the technical accomplishments of Chang'e 4, 5, and 6, the development of the Long March 9 heavy lift rocket, the demonstrated development of the Mengzhou crewed spacecraft, and the Lanyu lunar lander, has caused many of those analysts to revise their assessments upward. The Long March 9 is China's equivalent of the Space Launch System, a heavy lift vehicle designed to lift the mass required for a crewed lunar mission. It has not yet flown. Its development timeline has been revised several times. But the rocket is in active development, and the overall architecture for the Chinese crewed lunar mission, 2 Long March 9 rockets, one carrying the crewed spacecraft, Mengzhou, and one carrying the lunar lander, Lanyu, rendezvousing in Earth orbit before proceeding to the Moon, has been publicly described in sufficient engineering detail that it is credible as a real program rather than an aspirational statement. The Mengzhou crewed spacecraft is designed for a crew of 2 to 4 and is larger than Orion. The Lanyu lander is designed to carry 2 taikonauts to the lunar surface. Test versions of both vehicles have reportedly undergone ground testing, and the overall program timeline calls for an uncrewed lunar landing test before the crewed mission, again mirroring the approach NASA took with Artemis I before Artemis II. The 2030 target date for a Chinese crewed lunar landing, if achieved, would be before the NASA schedule for Artemis III, even on NASA's current optimistic projection. NASA's target for Artemis III, the first crewed lunar landing under the Artemis program, has slipped from its original 2024 target to a current official goal of no earlier than 2027 or 2028, with many analysts and the Inspector General projecting a date closer to 2029 or 2030. This means the scenario of China landing on the Moon first, before the United States returns, is not a fringe concern. It is a genuine possibility, perhaps even a probability under some scenarios. And the political and geopolitical implications of that outcome are substantial, in ways that go well beyond the question of who puts boot prints in the regolith first. The Moon's south pole is the most strategically important region of the lunar surface. It contains permanently shadowed craters that, based on data from multiple orbiters and the L-Cross impactor experiment, contain water ice, potentially in quantities large enough to support a sustained human presence, both for drinking water and for splitting into hydrogen and oxygen for rocket propellant. The nation that establishes a permanent presence at the lunar South Pole controls, in a practical sense, access to the most valuable resources on the Moon. This is not science fiction. It is a strategic reality that both the United States and China understand perfectly well. The Artemis Accords, a set of bilateral agreements that NASA has established with partner nations for responsible behavior in space exploration, have been signed by more than 40 countries as of 2024. China and Russia have not signed the accords and have announced their own competing framework, the International Lunar Research Station, a partnership between CNSA and Roscosmos that envisions a permanent robotic and eventually crewed presence at the lunar South Pole in the 2030s. The Artemis Accords are worth examining in more detail because they are doing something genuinely novel in the history of space law. the 1967 Outer Space Treaty, the foundational document of international space law, declares that the moon and other celestial bodies are the province of all mankind and cannot be subject to national appropriation by claim of sovereignty. This language was written in the context of the Cold War to prevent either superpower from simply planting a flag and claiming the moon. It has served reasonably well for 50 years when no nation was actually in a position to establish a permanent presence anywhere beyond Earth orbit. The Artemis Accords try to create a more practical operational framework for the era when permanent cislunar presence is actually imminent. They establish principles including transparent operations. Parties must announce their plans and activities. Interoperability of systems, spacecraft, and surface assets should be designed to work together for emergency situations. Sharing of scientific data, deconfliction of operations. Parties must notify each other of their planned activities to avoid interference. And, most controversially, the concept of safety zones around operational areas. A safety zone would be a designated exclusion area around an active operation, like a mining site or surface habitat, where other nations would agree not to conduct operations that might interfere with it. The safety zone concept stops well short of territorial sovereignty. It explicitly does not claim ownership of the lunar territory, but it effectively creates a framework for resource utilization rights that goes significantly further than the Outer Space Treaty. The Accords have been criticized by Russia and China as an attempt to create an American-led framework for governing the moon in advance of the actual legal regime being negotiated through the UN Committee on the Peaceful Uses of Outer Space, and therefore as an attempt to lock in American interests before the rules are formally established. This criticism has some merit. The Artemis Accords are, in effect, an attempt to establish practical norms through bilateral agreements faster than the formal multilateral process can move. The two competing frameworks, the Artemis Accords Coalition and the ILRS Coalition, represent the two sides of what is, in all but name, a new space race, and one with higher geopolitical stakes than the original. Chapter 9. The New Space Race. How tight is it? The original space race, the competition between the United States and the Soviet Union from the late 1950s through the early 1970s, was motivated by a specific geopolitical reality. The two most powerful nations on Earth, locked in an existential ideological competition, each trying to demonstrate the superiority of their system through technological achievement. The space race was, fundamentally, a proxy for the Cold War, and when the Cold War's dynamics shifted, when détente replaced confrontation as the dominant mode of US-Soviet relations, and when the political urgency of beating the Soviets to the moon faded after Apollo 11, the space race ended. The new space race is structurally different in several important ways. It is not purely a two-party competition. The United States, China, and increasingly a resurgent commercial sector are all operating in cislunar space with distinct agendas. India's Chandrayaan-3 mission successfully soft-landed near the lunar South Pole in August 2023. The first time India had successfully landed on the moon, and the first time any nation had landed near the South Pole specifically. Japan's slim lander reached the moon in January 2024, demonstrating precision landing capability. The European Space Agency has aspirations for a significant role in lunar exploration, including the proposed Lunar Gateway. Russia's Luna 25 lander, intended to reach the South Pole in August 2023, failed upon landing, a reminder that reaching the moon remains technically demanding. The field of lunar participants is broader than at any previous point in history. But in terms of the primary competition, the question of which flag flies first at the lunar South Pole on a crewed mission, it is, fundamentally, a US-China race. And it is a race that is considerably closer than the public discourse in the United States tends to acknowledge. The American side of the race has several structural advantages. NASA has more flight heritage in deep space than any other agency. The United States has already flown the SLS and Orion. The Artemis Accords coalition provides more international partners and more international legitimacy for the American program. SpaceX's Starship, if it continues its development trajectory, will provide the United States with a launch capability that dramatically exceeds China's Long March 9 in payload capacity. And the commercial space sector broadly, not just SpaceX, but Blue Origin, Rocket Lab, and others, gives the United States a depth of industrial capacity in space launch that China does not yet match. The Chinese side of the race has different but significant advantages. The Chinese program operates with a unity of political will and resource, direction that democratic systems have structural difficulty matching. China can make a decision to prioritize lunar exploration at the national level and sustain that prioritization across changes in leadership, in a way that NASA, whose budget must be renegotiated with Congress every year, cannot. The Chinese program does not face the same cost-plus contracting problems that have afflicted the SLS. China's aerospace sector operates under a different incentive structure, and while the Long March 9 development has its own challenges, the institutional dynamics are different. China also has a specific advantage in the timeline of its robotic precursor program. The Chang'e missions have built up a detailed database of the lunar surface environment, and landing site characteristics that is directly applicable to crewed mission planning. The data from Chang'e 7 and Chang'e 8 will inform the site selection and surface operations planning for the crewed mission in ways that NASA's precursor data does not yet provide for Artemis II, because the human landing system, Starship, has not yet demonstrated lunar landing capability. There is a dimension of the new space race that is almost never discussed in popular coverage, but that shapes the strategic context of everything else: the militarization of cislunar space. Both the United States and China have developed anti-satellite capabilities. China's 2007 ASAT test destroyed one of its own weather satellites, creating a debris field that still poses a hazard to spacecraft in that orbital regime. Both nations have developed satellites capable of maneuvering near and interfering with other nations' satellites. Both have developed electronic warfare capabilities that can jam or spoof satellite communications and navigation signals. Cislunar space, the volume of space between Earth and the Moon, is increasingly being recognized by military planners as a strategic domain that is currently ungoverned. and that confers significant advantages to whoever establishes presence there first. The Moon's surface, particularly the South Pole, provides line of sight to much of cislunar space, and to Earth-Moon space broadly. A radar installation on the lunar surface would have extraordinary coverage of cislunar space. A communications relay on the lunar surface would provide a persistent, hard-to-jam communication capability that Earth-based systems cannot match in some scenarios. None of this means the Moon is going to become a military base. The Outer Space Treaty prohibits placing weapons of mass destruction on the Moon and establishing military bases, fortifications, and weapons testing there. But it does mean that the question of who has a presence at the lunar South Pole first, and therefore who is in the best position to shape the norms and the practical realities of lunar operations, is not purely a scientific or commercial question. It is a question with genuine security implications that are being taken seriously by the strategic communities in both Washington and Beijing. This context does not make Artemis II more technically interesting, but it does make it more consequential. The mission that Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are preparing to fly is not just a scientific mission or a demonstration of technological capability. It is a statement at a moment when statements of this kind matter greatly about American capacity and will in the domain that is becoming the next frontier of strategic competition. The critical uncertainty on the Chinese side is the Long March 9. The rocket is central to the crewed mission architecture, and it has not yet flown. Developing a new heavy-lift rocket is one of the most technically demanding challenges in aerospace engineering, and the development timelines for every major heavy-lift rocket in history, including the Saturn V, the Space Shuttle, and the SLS, have been substantially longer than initial estimates. If Long March 9 encounters development challenges similar to those that have affected every comparable program, the 2030 crewed lunar landing target becomes 2032 or 2035, which is much more comfortable from a competitive standpoint for the United States. The critical uncertainty on the American side is the integration of Starship with the Artemis architecture. Starship needs to demonstrate that it can execute a lunar landing with the required precision, reliability, and life support capability in a crewed configuration before it can be trusted with the Artemis III crew. This requires not just the successful development of the Starship vehicle, but the successful demonstration of a specific crewed lunar lander variant, the human landing system version of Starship, which involves a unique propellant loading architecture, a specific crew access and egress mechanism for the lunar surface, and a landing capability at the South Pole, terrain that is distinct from what any Starship variant has previously attempted. If both programs hit their timelines, and neither is on a trajectory to do so, the outcome is close to a dead heat. If either program encounters significant delays, the other has an opportunity to pull ahead. The honest answer, from anyone with a realistic assessment of the situation, is that the outcome of the race between the United States and China to put humans at the lunar South Pole is genuinely uncertain, and that this uncertainty is more uncomfortable for the United States than its official communications tend to suggest. The political stakes of losing this race are not simply about prestige, though prestige matters. They are about control of the cislunar space environment and the lunar resources it contains, about the demonstration to American allies and potential adversaries of American technical and institutional capacity, and about the narrative of which model of political economy produces better outcomes in high-stakes technological competition. These stakes are not hypothetical. They are the actual geopolitical context in which the Artemis program is operating, and they explain why the program persists despite its extraordinary cost and its institutional difficulties. Chapter 10: The Commercial Disruption: SpaceX versus the Old Architecture. The most interesting internal tension in the Artemis program is not between NASA and China. It is between NASA and one of its own contractors. SpaceX is not a conventional aerospace contractor in the way that Boeing and Lockheed Martin are conventional aerospace contractors. It is a company with its own vision for the future of human spaceflight. A vision that includes a crewed mission to Mars, the colonization of Mars as a long-term goal, and a specific business model based on dramatically reducing the cost of access to space through reusability. The relationship between SpaceX and NASA is therefore not simply the relationship between a contractor and a client. It is the relationship between two entities with partially overlapping but distinct goals, where the contractor's long-term ambitions may ultimately make the client's chosen architecture obsolete. This tension became visible in the summer of 2024, when SpaceX achieved a series of milestones with Starship that dramatically changed the landscape of the program. In June 2024, Starship's fourth integrated flight test achieved a full-duration burn of the Super Heavy booster, followed by a successful propulsive landing of the Super Heavy booster in the Gulf of Mexico, using the chopsticks mechanism, the mechanical arms on the launch tower that catch the returning booster. The Starship upper stage completed its flight successfully and achieved a controlled splashdown in the Indian Ocean. For the first time, both elements of the Starship system had completed their missions successfully. The fifth integrated flight test, in October 2024, went further. The Super Heavy booster was caught by the chopsticks mechanism at the launch pad, not splashing down in the water, but returning to the launch pad and being physically caught by the tower. This demonstrated, for the first time, a key element of the full reusability architecture: the booster returning to its launch site to be refueled and relaunched without requiring significant refurbishment. The implications for launch cost were immediate and obvious. A booster that can be relaunched with minimal refurbishment, combined with a second-stage vehicle that is also designed for reuse, creates a cost structure that is fundamentally different from the expendable architecture of SLS. This creates an interesting dynamic for the Artemis program. SpaceX is under contract to NASA to provide the Human Landing System, a Starship variant designed to land on the Moon, and that contract is specific and bounded. But Starship's broader capabilities are already beginning to reshape the conversation about what the rest of the Artemis architecture should look like in the 2030s and beyond. Several members of Congress and several space policy analysts have begun asking publicly why the United States is paying $4.1 billion per SLS launch, when Starship may be able to provide comparable performance at a fraction of the cost. The question is not fully answerable yet. Starship has not yet demonstrated crewed flight capability, has not yet demonstrated the propellant transfer technology needed for the deep space architecture, and has not yet shown the reusability in practice over many flights that its projected cost assumes. But the trajectory is visible, and the trajectory points toward a future in which the SLS, built at enormous cost over 17 years, specifically to be the backbone of the American return to the moon, may be superseded by a commercial vehicle that emerged from a startup in a fraction of the time at a fraction of the cost. The commercial landscape around Artemis extends beyond SpaceX. Blue Origin, after losing the original human landing system contract to SpaceX, successfully protested the award, a protest that was ultimately dismissed by the Government Accountability Office, and subsequently won a separate contract for a second human landing system, the Blue Moon lander, in May 2023. This second HLS contract, worth $3.4 billion for the initial phase, gives NASA two independent commercial options for landing humans on the moon and reduces the program's dependence on Starship for this critical element. Blue Origin's Blue Moon lander uses different technology from Starship. It is a more conventional lander design, with a separate ascent stage and descent stage, rather than Starship's single integrated vehicle architecture. It is designed to work with the SLS/Orion/Gateway architecture, without requiring the in-space propellant transfer that Starship's architecture requires. In some ways, Blue Moon is the more conservative and predictable technical approach. In other ways, Starship's aggressive design goals make it potentially more capable if they are achieved. The existence of two independent commercial human landing systems, competing with each other for lunar mission assignments beyond the initially contracted missions, introduces a degree of healthy competition into the program architecture that has been largely absent from the government-led elements of Artemis. If both Blue Moon and Starship demonstrate lunar landing capability, NASA will have options for subsequent missions that were not available when the program began. This competitive dynamic is exactly what the Commercial Crew program achieved for low Earth orbit, where the competition between SpaceX and Boeing, though Boeing's development has been troubled, has produced better outcomes than a single provider approach would have. NASA's official position is that SLS and Orion will continue to be the primary crewed launch system through at least Artemis 5, the fifth planned mission, and possibly beyond. The agency notes that SLS provides specific capabilities that Starship does not currently offer, including a mature launch infrastructure, a proven crew capsule in Orion, and a launch trajectory that has been validated by flight test. These points are technically defensible in the near term, but the longer-term trajectory of the program is less certain. If Starship achieves the per-launch cost that SpaceX projects, and if it demonstrates the crewed deep space capability that the human landing system contract requires, then the economic logic of continuing to fly SLS, even for missions where both systems are technically capable, becomes increasingly difficult to defend. The program that was designed with SLS as its cornerstone may, by the end of the Artemis program, look less like the original design and more like a transition to a commercial dominant architecture. This is not a cause for alarm for the Artemis program's near-term goals. Artemis II will fly on SLS and Orion regardless of what Starship does, because the crew capsule is Orion and the only launch system designed to put Orion on a translunar trajectory is SLS. But it is a cause for honest reflection about what the architecture of American lunar exploration looks like in 2035 and beyond, and whether the investments made in the SLS era will look in retrospect like a necessary bridge to a more capable future or like a more expensive path than necessary. The deeper point is that the commercial disruption represented by SpaceX and Starship is not an isolated event. It is the leading edge of a structural transformation in the economics of spaceflight that is going to continue regardless of what any single program does. The era in which government agencies are the primary producers of launch vehicles for human spaceflight is ending. The question for programs like Artemis is not whether to engage with this transformation, but how to do so in a way that maintains safety and achieves mission goals while the transformation is occurring. Chapter 11: What Artemis II actually needs to prove, given all of this context: the mission profile, the crew, the heat shield problem, the cost, the geopolitical race, and the commercial disruption. It is worth being precise about what Artemis II actually needs to accomplish. Not what it would be nice to accomplish. Not what the program says it is trying to accomplish. What it absolutely must demonstrate for the Artemis program to be on a credible path to landing humans on the moon. The most fundamental thing Artemis II needs to prove is that Orion is safe to carry humans beyond low Earth orbit. This sounds obvious. It is, after all, a crewed mission. But the specific conditions of Artemis II make this demonstration more demanding than it appears. The spacecraft will carry 4 people through an environment that no human has experienced in 52 years, using systems that have been tested exactly once in the flight environment, facing a heat shield that exhibited unexpected behavior on that test flight. The mission cannot fail on any of its primary life-critical systems. But Artemis II is also a test flight. Officially, it is the crewed test flight phase of the Artemis program. The crew's job is not just to survive the mission, but to evaluate the spacecraft, identify anomalies, characterize the systems, and bring back the operational data that will inform the design of subsequent missions. This is the classic test pilot role. The reason that Wiseman and Hansen, both test pilots by background, are on the crew. They are going beyond Earth orbit specifically to assess whether the system that took them there is ready to do it again, reliably, for more demanding missions. The specific test objectives for Artemis II include evaluation of the Orion life support systems under crewed conditions, including how the environmental control system performs, with 4 crew members breathing and generating moisture, and CO2 for 10 days. Evaluation of the communication systems at lunar distances, including the quality and reliability of voice and video communications through the deep space network. Evaluation of the crew's ability to perform manual operations, including manual approach and attitude control exercises that are planned for the mission, even though they are not necessary for the nominal automated flight, and evaluation of the launch abort system's readiness indicators, which cannot be fully tested without a crew on board, even if the abort itself is never used. Most critically, Artemis II will generate operational data on the re-entry and heat shield performance under crude conditions. The mission's re-entry profile will be slightly different from Artemis I's profile, incorporating whatever trajectory modifications have been made in response to the heat shield investigation. The post-flight analysis of the heat shield after Artemis II will be the most important data product of the entire mission from a program perspective. It will either confirm that the modifications are effective and the heat shield performs as designed, or it will reveal additional unexpected behavior that must be addressed before Artemis III. The mission also needs to prove something about the crew, about the human capacity to operate effectively in the deep space environment after 52 years, during which no one has done it. The psychological, physiological, and operational dimensions of sending humans beyond the protection of Earth's magnetic field at distances where emergency return takes 3 days rather than 3 hours, with communication delayed by increasing light travel time, are not fully characterized from operational experience. The Apollo program built that experience rapidly through successive missions. The Artemis program is starting from scratch, and Artemis II will generate the first operational experience with a human crew in deep space in over 5 decades. The mission additionally needs to prove something about the program's management, that NASA and its partners can execute a complex, multi-year, crewed spaceflight program in the current institutional and commercial environment, manage contractor relationships across a system as complex as Artemis, respond appropriately to anomalies, like the heat shield, without either suppressing information or losing the nerve to fly, and deliver a successful crewed mission that justifies the approximately $25 billion spent on SLS and Orion development. This is not a technical objective. It is an institutional one, but it is every bit as important to the program's future as the technical objectives. If Artemis II succeeds, if the crew returns safely, the heat shield performs as modified. The Orion systems demonstrate they are ready for the demands of Artemis III, and the program's management demonstrates the competence to execute a crewed deep space mission. Then the case for the Artemis program's continuation is significantly strengthened. Not just politically, though political support matters, but technically and institutionally. Success on Artemis II removes the largest single uncertainty overhanging the program, which is the question of whether the Orion spacecraft can safely carry humans through the re-entry regime that a lunar return requires. If Artemis II fails, if there is an anomaly serious enough to endanger the crew, if the heat shield behaves unexpectedly again in a way that requires a major redesign, if the mission is scrubbed for technical reasons and delayed by additional years, the consequences extend far beyond the immediate mission. A crewed mission failure at this stage, 50 years after Apollo and after $25 billion in development, would be one of the most consequential setbacks in the history of American space exploration, not just for Artemis, but for the broader case that government-led human spaceflight is still a viable and worthwhile investment. The stakes are genuinely high, not in an abstract or rhetorical sense, in the specific, concrete sense that the outcome of this mission shapes what American human spaceflight looks like for the next decade and potentially beyond. Chapter 12. The future of Artemis. If it works, assuming Artemis II is successful, which based on the engineering work being done and the professional quality of the people doing it is the most likely outcome. The program moves to Artemis II, and the stakes immediately escalate. Artemis III is the first crewed lunar landing under the Artemis program, and it involves a mission profile substantially more complex than Artemis II. The crew of 4 launches on SLS/Orion on the same translunar injection trajectory used for Artemis II. But instead of a simple free return flyby, the crew enters the near rectilinear halo orbit NRHO, a specific orbit in cislunar space that is gravitationally balanced between the Earth and the Moon, providing a stable staging point from which to conduct lunar surface operations. In the NRHO, the crew rendezvous with the Human Landing System, the Starship variant that will have been launched separately and is waiting in the NRHO for the crew. 2 of the 4 crew members transfer to the Human Landing System, descend to the lunar surface at the South Pole, conduct approximately 6.5 days of surface operations, return to the HLS, ascend to the NRHO, and rendezvous with Orion. All 4 crew members then return to Earth on Orion. The surface operations, the actual time on the Moon, will include geological sample collection, deployment of scientific instruments, testing of life support equipment, assessment of the landing site environment, and potentially the first steps toward evaluating water-ice accessibility in the permanently shadowed craters. This is a substantially more complex mission than Artemis II in several ways. It requires the Starship Human Landing System to have been developed, tested, and flight demonstrated in the crewed lunar landing configuration, a development challenge that is significant given Starship's current status. It requires the crew to perform a rendezvous and docking maneuver in cislunar space at the NRHO, a maneuver that has never been performed before at that orbital location. It requires the surface operations to be conducted in a radiation environment, thermal environment, and surface terrain that has never been experienced by any human being. The long-term vision for Artemis beyond the initial landings envisions a sustained human presence at the lunar South Pole, multiple missions per year, eventually leading to a permanent outpost. The Lunar Gateway, a small space station in the NRHO, is intended to serve as the hub for this sustained presence. South, staging point for crew transfers, a platform for long-duration research, and eventually a relay station for communication with Earth and with surface operations. The Gateway is being developed as an international collaboration, with NASA providing the power and propulsion element built by Maxar Technologies, the habitation and logistics outpost built by Northrop Grumman, and the Halo module, while ESA provides the international habitat, JAXA provides the Lunar Rover Lunar Cruiser, and the Canadian Space Agency provides the Canadarm3. This international architecture reflects one of the most important differences between the original space race and the current one. The United States is pursuing its lunar ambitions explicitly as an international coalition, while China is pursuing its ambitions through a narrower set of partnerships, primarily with Russia. The Artemis Accords framework, bilateral agreements that over 40 nations have now signed, establishes principles for responsible behavior in space that are designed to shape the norms of the cislunar environment in ways consistent with American interests. This is not just science diplomacy. It is geopolitical positioning, and it is happening in parallel with the technical program. The Artemis program's envisioned timeline, Gateway operational in the late 2020s, sustained lunar South Pole operations in the 2030s, is ambitious by any standard. It requires a level of funding stability and political will that the history of NASA programs suggests is difficult to maintain over decade-plus timescales. Every NASA administrator since Michael Griffin has faced the reality that the ambitious plans of one administration are frequently modified, scaled back, or redirected by the next. The Constellation program, the previous iteration of NASA's lunar return ambitions, canceled in 2010 by the Obama administration, is the most recent example of a program that accumulated years of development and billions of dollars before being redirected. The Artemis program has more political resilience than Constellation did, for several reasons. The geopolitical competition with China creates a bipartisan case for the program that was absent in 2010, when the rationale was primarily scientific and exploratory. The commercial involvement of SpaceX and other companies creates industrial stakeholders with political constituencies that extend beyond the traditional aerospace companies and their congressional allies. And the public visibility of the historic crew, the first woman, the first Black astronaut, the first Canadian beyond LEO, creates a broader constituency of people who have a personal investment in seeing these specific individuals complete their mission. But political resilience is not the same as certainty. The Artemis program's budget has been under pressure in every congressional cycle since its inception. The program's Inspector General has repeatedly noted that the pace of the program is constrained by funding levels below what the schedule requires. Any significant budget reduction or any programmatic failure that triggers a major investigation and redesign could delay the timeline substantially. A specific and underappreciated dimension of a successful Artemis II is what it does for the international partners. The Canadian Space Agency's involvement through Jeremy Hansen is not just a diplomatic courtesy, it reflects a genuine commitment by Canada to the long-term Artemis architecture, including the Canadarm3 that will be installed on the Lunar Gateway. A successful Artemis II strengthens the political case within Canada for continued investment in the Canadian contribution to the Gateway and beyond. The same logic applies to ESA, whose European service module has now been relied upon twice, Artemis I and, upon success, Artemis II, as a critical element of the Orion spacecraft. A successful mission validates ESA's contribution and strengthens the case for European investment in subsequent mission elements, including the international habitat for the Gateway. The international dimension of Artemis is often underweighted in assessments of the program's strategic value. The United States is not simply sending humans to the moon. It is building a coalition of allied nations around a specific vision for what the cislunar environment should look like. Every nation that signs the Artemis Accords, every international partner that contributes hardware or personnel to the program, is making a political choice to align with the American-led framework for lunar exploration rather than the Chinese-Russian ILRS alternative. A successful Artemis II reinforces that alignment. A failure or a prolonged delay that allows the impression to develop that the American program is struggling creates an opening for the alternative framework to attract partners who might otherwise have stayed with the Artemis coalition. This is not to say that the mission's success or failure will pivot international space policy overnight. These decisions are made over years, not months, and the relationships involved are complex and multidimensional. But the momentum of a successful crewed lunar flyby, the images of 4 historic crew members at the moon, the demonstration that the Orion spacecraft can safely carry humans through the deep space environment, these create a narrative that strengthens the coalition around the American program in ways that no amount of diplomatic communication can match. The most honest assessment is this: the Artemis program is on a path that, if followed without major disruption, leads to the first crewed lunar landing since Apollo 17 in approximately 2028 to 2030. That path requires Artemis II to succeed, requires the Starship human landing system to complete its development and demonstration, requires the program to resolve the heat shield anomaly definitively, requires the funding to remain at or above current levels, and requires the management of an extraordinarily complex multi-stakeholder program to hold together across changes in administration and congressional leadership. Every one of those requirements is achievable. None of them is guaranteed. Conclusion? Why this matters more than the hype. There is a way of telling the Artemis II story that makes it sound like a triumph. And it is, in many ways, a triumph. 4 extraordinary human beings, including a Black astronaut and a woman and a Canadian, will travel farther from Earth than any human in more than half a century on the most powerful rocket ever successfully flown, in the most capable crewed spacecraft ever built for beyond LEO missions, as part of a genuinely international effort to establish a sustained human presence at the moon. That story is true. It is worth celebrating. But there is another story being told simultaneously, and it is the one you need to understand if you want to know what is actually happening in space exploration right now and what is actually at stake. The other story is that the program carrying those 4 extraordinary humans to the moon has a heat shield that failed in a way that its engineers did not predict. And the investigation into why is one of the most consequential pieces of work being done in aerospace right now. The program costs $4.1 billion per launch for a rocket that flies once and is then discarded, at a time when a competitor rocket is being developed that may reduce that cost by orders of magnitude. The program has spent $93 billion to get to the point of 1 crewed lunar landing in a geopolitical environment where that landing may happen at roughly the same time as a competitor from a nation with a different vision for the future of the lunar surface. The 2 stories are not in contradiction. They are the same story, and understanding both of them is what understanding Artemis actually requires. What Artemis II represents, stripped of both the triumphalism and the cynicism, is the moment at which 50 years of accumulated capability, 50 years of computational advances, materials science, life support engineering, precision navigation, and the hard-won institutional knowledge of what goes wrong when you leave Earth orbit, is being assembled and tested against the hardest environment in human space flight. The people doing it are some of the best trained and best qualified people on Earth. The hardware they are using represents the current state of the art in crude spacecraft design. The problem they are solving, returning humans to the moon safely, reliably, and eventually routinely, is one of the most important problems that humanity is working on right now, not just for scientific reasons, but for the specific reason that the moon and cislunar space are becoming a domain of strategic competition, and the question of who dominates that domain will shape the broader trajectory of human civilization's expansion beyond Earth. The heat shield problem is not a minor footnote. It is a reminder that the frontier does not yield easily, that even the most carefully designed and tested systems can behave unexpectedly at the boundary of human experience, and that the courage required to fly a spacecraft that has exhibited unexpected behavior is not hypothetical. It is being exercised right now by 4 specific people who have made a specific choice: Victor Glover, Christina Koch, Reed Wiseman, Jeremy Hansen. They know about the heat shield. They have been briefed on the investigation, on the proposed mitigations, on the residual uncertainties. They are test pilots and mission specialists by training, and part of what that training means is that you understand the risk, you evaluate the mitigation, and you make the decision about whether the risk is acceptable for the mission. They have made that decision. That decision, and what it represents about human willingness to accept risk in the pursuit of understanding and exploration, is the part of the Artemis II story that tends to get lost in the coverage of costs and delays and geopolitical competition. The costs are real, the delays are real, the competition is real, the institutional dysfunction is real, and the 4 people who are going to climb into that capsule anyway, fully informed, and travel farther from Earth than any human being in 50 years, are also very, very real. The last time a human being left Earth orbit was December 1972. The next time will be whenever Artemis II flies. And the gap between those 2 moments, 50 years of technological progress, geopolitical change, commercial disruption, and institutional struggle, is exactly the scale of the undertaking that Artemis II represents. It is not just a mission, it is the resumption of something that was interrupted for reasons that had nothing to do with whether humanity was capable of doing it, and everything to do with whether humanity had the will to keep trying. That interruption cost us 50 years. In those 50 years, the world changed in ways that make the challenge of returning to the moon simultaneously easier and harder than it was in 1972. Easier because the computers are better, the materials are better, the understanding of the space environment is better, and the commercial sector has developed capabilities that the government could never have built alone. Harder because the institutional memory of deep space operations has largely faded, because the cost structures of traditional aerospace, contracting, have ballooned in ways that limit the pace of the program, and because the geopolitical context has added urgency that makes every delay feel more consequential. The 50-year gap between Apollo 17 and Artemis II is not just a historical coincidence. It is the result of choices, budgetary choices, political choices, strategic choices that future generations will evaluate against the backdrop of where those choices left the United States, at the moment when returning to the moon became urgent again. Understanding those choices and their consequences is part of what makes the Artemis II story something more than a celebration. The will is back. The machine is almost ready. 4 people are waiting. For reasons that had nothing to do with whether humanity was capable of doing it, and everything to do with whether humanity had the will to keep trying. The will is back. The machine is almost ready. 4 people are waiting.